This session, the continuation of the efficiency regulations. These are the figure of merit of a transformer. That is, based on the efficiency regulation, can judge the behavior of the transformer, whether it is efficient, whether it's the voltage regulation is better, or it is the voltage regulation is too high. Then to look into these two factors, we are continuing with the efficiency and regulation of the transformer. Once again, you can recall in the last session we discussed already about the efficiency of the transformer. Basically, there are two types of the losses they are occurring in the transformer. That is core loss and the copper loss, where the core loss is a constant irrespective of the load, whereas the copper losses are the variable. As the load varies, the copper losses are the vary. Because of these losses, there is a heat is dissipated in the transformer. It is producing the heat, so that there is a rise in the temperature of the transformer. Then, in general, the efficiency of the transformer can be defined in different way. It is basically the output power by the input power. Or you can express this efficiency in terms of output and the losses, or input and losses. Because we know the output of the transformer, that is how much you are loading the transformer, then you can go by the adding the losses to the output. What you are getting is the input, that is output plus losses. Therefore, the basically efficiency is the input. Therefore, the input what you are getting is output plus the losses. Here there are two types of losses. This loss can be written as copper loss and the core loss. Then also there are the equation for the efficiency of the transformer. We know that we have seen that from no load to full load condition, the core loss remains constant. However, the copper losses are varying as the load varies. Also, in the last session I told you that is a transformer is rating in terms of kilovolt amperes, or a bigger unit of megavolt ampere. That is represented by S. Now I am considering here kVA. Then degree of loading, that is the loading of the transformer, whether it is a full load or a half load or a 3/4, that is represented by a letter X. X determines the loading factor. Then the transformer is delivered at any given point of time is X times S. That is kVA output of a transformer at any given load X is X into S. If the power factor of the load is a cos phi, we know that the product of kVA and the power factor is the kilowatt. The product of kVA and sin phi is given kVAR, that is reactive power. What we are interested is the output power. Therefore, if we are multiplying cos phi to kVA, then what I am getting here is the output power in terms of kilowatt, because my output is in terms of kilovolt ampere. Multiply cos phi, therefore what I am getting is output power is in terms of kilowatt. How we are getting? It is a loading factor multiplied by kVA multiplied by the power factor of the load. And the copper loss at full load, that is the corresponding X is equal to 1, because we are using X is equal to 1 for full load, X is equal to half for the half full load, X is equal to 1 by 4 for 1/4 full load. If it is 60% of the full load condition, we are putting X is equal to 0.6 and so on. Therefore, the copper loss at full load is what I am representing here is WCUFL, substitute to CUFL, that is the copper loss at full load condition. Then the copper loss at any load X is proportional to the square of the loading effect. Therefore, it is X square times copper loss at full load. That is the copper loss at any load X is X square times copper loss at full load, and the iron loss remains constant, that is equal to Wi. Now I am using here two expression. One is when S is kVA, in that case your iron loss and copper loss should be in terms of kilowatts. Therefore it is X into S into cos phi, and that is the output. That is once again it is the output plus iron loss plus copper loss. If you are using S as a kVA, then you have to make use of Wi and WCFL is also in terms of kilowatts. Otherwise, straightforward equation, you are using this formula, that is x into s into 10 to 3 into cos phi, because I am multiplying 10 to 3 because s is in terms of kilovolt ampere, where x is loading factor. Here the iron loss is Wi and the copper loss at any load x is x square time WCFL. However, in this case, both Wi WCFL are in terms of the watts. This is how we are finding out the efficiency of the transformer. Then if you are going for the regulation means the change in the voltage across the terminals of the load from no load to full load. That is what the consumer or what we are desire is the voltage across load remains the constant. As such, there should not be any variation of the voltage across the load. However, because of the drops in the transformer, that is in the form of resistive drop as well as a reactance drop, as the load increases, because the drops are proportional to product of resistance and current, resistance and reactance. As the current increases, because reactance and resistance are constant, however, as the load increases, that is a factor I is increasing, then product of IR and IX is also increasing. Because of that, the voltage which is available across the load goes on decreasing as the load increases. But what we are expecting, the good transformer is that the variation of this voltage from no load to full load is very as small as possible, so that it has got a very good regulation, what we are calling. Means ultimately what we require is the constant voltage, almost constant voltage across the load. That is the importance of the regulation. Okay. Therefore, the output voltage in the transformer will not be maintained. Voltage in the transformer will not be maintained constant from no load to full load condition for the fixed input voltage in the primary. Even though if you are keeping the voltage input voltage constant, it is not possible to maintain the constant voltage across the output because of the drops in the transformer. The same thing is having here. This is because there will be internal voltage drop in the series leakage impedance of the transformer. That is a impedance means it is a combination of resistance and reactance. The magnitude of which will depend upon the degree of the loading as well as the power factor of the load. That is, the drop in the transformer is depending upon the magnitude of the current I and the power factor. The knowledge of the regulation gives us idea about change in the magnitude. How much there is a change in the voltage from no load to full load, that you come to know when if you are studying the regulation. Idea about the change in the magnitude of the secondary voltage from no load to full load condition. Suppose the no load and the load voltages are respectively VO2 and V2. V2 is the voltage across the load. VO2 is, suppose if you are disconnecting the load, if you are measuring the voltage across the terminals of the transformer, then what voltage we are getting is VO2. That is what we are calling is no load voltage. No load voltage. As the load connected, then the voltage VO0 is goes on changing because of changing the load current as well as the power factor. Therefore, the change in the magnitude of the secondary voltage, that is VO2 minus V2. Therefore, this change is expressed in the percentage with respect to the rated terminal voltage across the secondary of the transformer, that is V2. This change is expressed as the percentage of the no load secondary voltage or the load voltage to express a regulation. Usually, the lower value of the regulation will ensure lesser fluctuation. If the difference between V0 to V02 to V2 is less, means the drop in the transformer is less, therefore it has got a better performance. Means almost all the voltage we are getting a constant voltage. Therefore, if the transformer is ideal, we don't have any voltage drop. Therefore, what we are getting is VO2 is equal to V2 we are getting. Okay. Therefore, the percentage voltage regulation usually defined as it is a change in the voltage from no load to full load to no load voltage. That is VO2 minus V2 divided by VO2. This is how we have to calculate the regulation. Then we will consider the transformer which is represented referred to the secondary. You are transferred all the resistors and reactance to the secondary side. Then I am representing this RO2, this is XO2. The current which is delivered is I2. The V2 is voltage across the load, whereas the VO2 is the input voltage here. If there is no load is connected here, in this case VO2 is equal to V2. VO2 is equal to V2. As such, there is no difference between VO2 and V2 because there is no current will flow. If the load is not connected, there is no flow of current, there is no drop in the resistance as well as the reactance. As the load increasing here, if you are the load if you are goes on increasing, then the current I2 is increasing. If the I2 is increasing, I2 RO2 is increasing, I2 XO2 is also increasing. Because of that, there is change in the voltage between VO2 and the V2. That change in the voltage we are expressing in terms of VO2. That what we are calling is the voltage regulation. Then we look into the vector diagram for this one. Then we will derive the equation for the voltage regulation. That is, we know that if you want to express VO2 in terms of V2, what you have to do is for this V2 you have to add I2 RO2 and IOXO2. Then what I am getting is VO2. Already we have seen this. VO2 is equal to V2 plus I2 RO2 plus JXO2, or it is V2 plus I2 ZO2. That is combination of RO2 and XO2. What we are calling is the impedance of the circuit. Then if you look into the vector diagram, this is a V2 that is taken as a reference. The I2 is lagging by an angle of 5. Then to the tip of V2, what I have to add is I2 RO2. This I2 RO2 is parallel to I2. That's I am showing here. Just you can see here. This is parallel with I2. Just it is where we are adding, it is a tip of I2 RO2 because it is I2 RO2 is adding to V2. Then this for I2 RO2, what I am adding is I2 XO2. I2 XO2 which is perpendicular to the I2, or it is perpendicular to I2 RO2. That is also I am demonstrating here. See here, it is I2 XO2 is perpendicular to I2 because it is inductive drop. The current I2 lags this voltage by an angle of 90 degree. Once again I have got I2 XO2 here. Then if you are adding V2, that I2 RO2 to I2 XO2 to V2, then what I am getting here is I2 ZO2, that is the impedance drop. Therefore, the total voltage VO2 is sum of V2 plus IO RO2 I2 XO2 into VO2. That is what we are getting is VO2. This is a vector sum of all these drops plus V2. What I am getting is VO2. Therefore, this is how we are calculating. And for the different power factor, we are already taken V2 is taken as a reference. For lagging power factor, you have to take it as a -5. For leading power factor, you have to take it as a +5. Then phi is equal to 0, you have to take it for unity power factor. The same thing is explained here. That is V2 an angle of 0 degree, so -5 because it is a lagging power factor. Then for unity power factor, the value of phi is 0. Therefore, substituting the values, what I am getting here. Then similarly, I have got for a leading power factor, that is I2 is +5. Then what I am getting is VO2 is equal to V2 0 plus I2 an angle of 5. RO2 plus say XO2. This is how we have to calculate V2 directly. Otherwise, if you want to express our V2, that is the regulation is, once we know the VO2 minus V2 minus VO2 into 100. What I am getting is the regulation. Then for lagging power factor, then once again, if you are interested in the voltage in terms of I2, RO2 and cos phi, just I explained in the while explaining the equivalent circuit diagram, I have got a V2 to that I2 RO2. I am resolving this into X and Y component. To that I am adding I2 XO2. Then once again I am resolving this into I2 XO2 X component and Y component. Then finally what I am getting is I2. What I am getting here is the VO2. Then I want VO2 in terms of V2, I2, RO2 and cos phi and sin phi. Just I am making the construction lines here, that is a DH and dashed line, and resolving this I2 RO2 into its X component and X component and Y component, that is BD and DC. Also I am resolving I2 XO2 into its CG as the X component, GH as GF as the Y component. Then ultimately what I am interested is AF square. The AF square what I am getting here is from AH square plus HF square. The same thing is explained here. That is what derived this equation in the case of while manufacturing the equivalent circuit diagram of the transformer. That is, it is you are getting from the triangle BCD and BCD, and what you mean by AB, BD, DH, that we are getting from this, the values from this resolving the component of X and the Y component. Ultimately, that is VO2 square, that is VO2 square, what I am getting is, that is a V2 plus I2 RO2 cos phi, that is a BD, then DH is I2 XO2 sin phi, it is a whole square, plus it is the total is FG is I2 XO2 cos phi. In that what I have to deduct is HG, that is I2 RO2 sin phi, that I am getting here I2 RO2 sin phi from this triangle. Ultimately, if we are substituting and simplifying, taking the square root of this, then what I am getting here is the value of VO2. Then we can put for percentage regulation, that is VO2 minus V2 divided by VO2. Then you have to substitute the value of V2 here, that is V2 plus I2 RO2 cos phi plus I2 XO2 sin phi. Then this minus V2 is as it is divided by VO2. This VO2, this V2, this V2 and this V2 get cancelled. Then the equation for percentage regulations, what we are getting is I2 RO2 cos phi plus or minus I2 XO2 sin phi divided by VO2 into 100. I am using here plus and minus sign here. The plus sign you have to take if it is a lagging load, and you have to take a minus sign as for the leading load. Then the cos phi you have to take it as the 0 for the unity power factor. This is how you have to calculate the regulation of the transformer.